So now you've learned about sequential circuits. We started with latches, and then we moved to flip-flops, and then we started using those flip-flops to create really interesting circuits called finite state machines. Now if you notice, we used this clock signal in a flip-flop and a finite state machine, but we haven't really talked that much about the clock. So let's start this lecture by talking about the clock. So a clock is typically a periodic signal. So here's my clock signal, and it's not going to look super periodic because I don't have a grid here to help me draw this, but it looks pretty even. So this would be a periodic signal in that there's a regularity to it, periodic. If it was not periodic, then my signal would probably look something like this, where each section is a little bit different, and this is not periodic. So we can explain a bunch of properties about a periodic signal, such as a clock. So let's just look at this right here. We can call this a period. From this point in the signal to this point in the signal. This is one period, and then it repeats itself. There's another period, and then it repeats itself, another period, etc. Alright, then we also have the time that the signal is high. So we're going to call this T sub h for the time it's high. So how is this going to be useful for us? Well, we also have something called the frequency. The frequency of a signal, of a periodic signal, is 1 over the period. Then we also have something called the duty cycle. And the duty cycle is equal to the time that it's high over the period. It's typically represented as a percentage. So in my drawing, it looks like we have a 50% duty cycle because the time that it's high is the same as the time that it's low. But let's say I had a signal that looked like this. So what I tried to draw here is that the time is high is a quarter of the period. So here this would be a 25% duty cycle. Alright, so let's do a couple of math problems related to these variables. I'll open up the text here. We're looking at chapter 31. So here's again a picture of a periodic and an aperiodic or non-periodic waveform. We have a period T shown here. We have the equations I just wrote down. T is 1 over the frequency, or frequency is 1 over the period. Here's our first example. So a given waveform has 40 nanosecond period. What is the frequency of this waveform? So we do frequency is 1 over the period, so 1 over 40 nanoseconds. Nano stands for 10 to the minus 9. So you punch this in your calculator and you're going to get 25 times 10 to the 6 hertz. 10 to the 6 is mega, so this is 25 megahertz. Alright, here's another example. If we have a 50 megahertz frequency, what is the period? Well, period is 1 over the frequency. So period is 1 over 50 megahertz, 50 times 10 to the 6. And that gives us 20 times 10 to the negative 6 seconds. And 10 to the negative 6 is a micro, so we have 20 microseconds. Then we're going to look at the duty cycle. A waveform with a 25% duty cycle is high for 12.5 nanoseconds. Find the frequency. Well, if it's high for 12.5 nanoseconds, and that's a quarter of the period, that means the other 3 quarters, it's low, so the total period is going to be 4 times this amount. So 12.5 times 4 is 50, so we're going to do 12.5 over 50 gives us the 25% duty cycle, and 50 nanoseconds, if we take the reciprocal of that, it's going to be 1 over 50 times 10 to the minus 9, and that comes out to 20 times 10 to the 6, or 20 megahertz. Alright, so why did we just spend all this time figuring all this stuff out about clocks? Well, remember how we talked about delays in combinatorial circuits? Well, there's also delays in sequential circuits. And these clock properties are going to come in handy. I will explain that in the next lecture.